Oh, my first serious course on quantum mechanics. Because you see, when you study quantum mechanics at least in the usual presentation, people don't explain to you what the state vector or the wave function means. And then they say something like, we don't study nature, but what we can say about nature, which is more or less we don't speak about the world, but about our knowledge of the world. That's the way they say it, and which is more or less derived from Bohr. And that's really what the people told me, and I was really told that. And I thought it didn't make any sense, because of course if you speak of our knowledge of the world, and you have a knowledge of the world, therefore that knowledge speaks about the world, so the sentence didn't make any sense. And then I was bothered by it right away, right from the first courses. I noticed that many students are so much bothered by the mathematics that they don't ask any question. I mean, they want to know how to compute the spin in one direction if you know it in the other direction, etc. But the exams, I don't think they were very demanding in my time. I don't think the technical thing actually I knew so well, but the philosophy bothered me right from the beginning. There was another student in my class, and we started discussing that, and we're still discussing that now because he has also become a professor. And so I started to be bothered. But then I misunderstood what the problem was. Like many other people, I thought it was a problem that the mathematics are not well defined, and so I went to work on something which was supposed to make the mathematics better defined, and of course that didn't solve any problem. And then I was told that a certain Mr. Bell had shown that quantum mechanics cannot be completed, that hidden variable theories are impossible, and so on and so forth, and I left the subject. And I came back to it when Shelley Goldstein, when I was at Rutgers, and he got interested in so-called hidden variable theorem, Bohmian mechanics, but basically before that it was Nelson's stochastic mechanics. And Nelson also gave up his own. It's very interesting. Nelson was one of the person who revived the interest in these hidden variable theories, independently of, or at least in parallel to Bell, but he also, when he realized that his theory was non-local, he gave up his theory, and it was a great confusion among us when I remember that when he spoke about that. And Shelley really rekindled my interest in that by, talking about it and clarifying things. Of course, I learned a lot by going to Rutgers and talking to him, and of course also Detlev and so on and others. But that's how I got to know the subject. And of course I read Bell's book when it came out and so on, but that's a later story. But I guess there is something strange. I mean, there is obviously something strange about the theory, and otherwise we wouldn't be discussing it so long after it being invented. And the way it's presented should be shocking to students. So I was bothered right from the beginning, but I didn't see any solution, because on the one hand they tell you this sort of Copenhagen stuff, and they tell you there is no alternative, okay? And that's not true. Well, quantum mechanics is supposed to be, the foundation of all of physics, and therefore in principle of all of science, because it's a fundamental theory of atoms, molecules, electrons, quarks, and so on. So it's sort of at the bottom of all the physical theories. But then the question is, since the way it is formulated usually, it always tells you what will be the prediction of the theory when you do measurements, but it never specifies what a measurement is, although in practice we know what it means. So the question is, it's not a question, I don't want even to formulate it the way people do with Schrödinger's cats and so on, but it's rather that, what do you mean by the wave function? What do you mean? What's the meaning of the state vector? And if it's only a recipe to compute result of measurement, then it's very difficult to take it seriously as a fundamental theory, because who was the measurer during the dinosaurs time? Or does it mean that quantum mechanics applies to a measurement, but there's nothing in the tree there? Or, I mean, it just doesn't make any sense to say that a fundamental physical theory has, of course, if any theory will have to be checked by measurement, but it's not the same thing that to say you check them by measurement or by observation, and saying that it's about measurement doesn't have any meaning outside of measurement. So the question is, what you need something to tell. You need, to tell a theory about the world, which is not whose fundamental concepts are not expressed, the meaning of the concept is not expressed in terms of measurement. That's the basic point. And as far as I'm concerned, there's only one theory which I really find complete in quantum mechanics, which is Bohmian theories, the Breuil-Bohm theory. Because this gives an account of what's going on. It just says the obvious thing. I mean, the wave function is there and it guides the particle, and so the particle moves in a certain way, and you find the particles wherever the theory tells you you're going to find them, and that's what you observe. So I don't agree with people who say that, for example, quantum mechanics and Bohmian mechanics are different theories, because quantum mechanics is simply not a theory about the world. It just says it's not a theory about the world, and unless you, I mean, of course, some people interpret it naively. So, for example, if an electron comes and you measure the spin in one direction, then they may think you have found what was the value of the spin before you measure it. Okay, you just discover what the energy really is, what the angular momentum really is. But that's what one might call naive realism, and that's usually, there is a subtle theorem which is due to Cocken, Specker, and Bell, which shows that this can't be taken seriously, because you can show that if you just assume that for sufficiently many observable, that the values are predetermined before the measurement, then you run into contradictions. And contradiction not just because of the structure of the theory, but just the data are incompatible. The data that you observe are incompatible with the mere assumption that they are predetermined independently of the measurement. So the measurement must play an active role. And if you don't have a theory of what's going on in the world without a measurement, then you can't understand how the measurement plays an active role. So the very thing which people say, oh, but the measurement disturbs the system. But it can't disturb the system if there is no system. The meaning of what the system is given by the measurement. You see, the measurement is really, as long as it plays a central role, you can't understand the measurement, because the measurement is there at the basic of your discourse. And so you need something, and the only thing which I find consistent and attractive, which completes quantum mechanics, is Bohmian mechanics. But of course, Bohmian mechanics has a peculiar feature that it sort of describes the world in terms of matter in motion, so particles actually do move and they are guided by the state vector. But then the peculiar thing is that you can sort of, as far as concrete predictions are concerned, as far as practical applications are concerned, those trajectories don't play much of a role. You can just forget them in practice. You do statistical predictions. Statistical predictions are those of quantum mechanics and the application to technology and so on. They all work without worrying about that. So you can forget about them. But it's not the same thing as forgetting about them when you know that they exist and forgetting about them when you don't know that they exist. Because if you don't know they exist, you run into all kinds of conceptual problems. You're trying to make sense of a theory which is manifestly incomplete. If you know that the trajectories are there, then you understand there are no mysteries about quantum mechanics anymore. And then, at least none of the mysteries that are usually in the books. And then you just, you're happy, you live happy thereafter. I mean, you just remember that they are there, and you don't worry, you don't need to compute them or worry about them any, but you don't run into these conceptual problems, which people have been talking over and over again. Then, of course, people always say there are competing theories, but to Bohmian, but I don't really agree with that. I think there are many proposals, like decoherent histories, many worlds, etc., which really don't get off the ground, in the sense that those proposals run into insuperable difficulties, in my view. And then there is the so-called Gerhardt-Rimini-Weber theory, GRW, which of course can be defended and saying that they don't run into difficulties. But they are extremely counterintuitive when you go to the consequence of that. For example, on one version, you have a piece of matter over there, a piece of matter over there, which are never observed because they are like half a particle. And by observing on one side, you can switch the whole of matter from one side to the other instantaneously. That's very counterintuitive, to put it mildly. On that account, for example, there are nucleus, there is no nucleus, there is no electron, the particles don't really exist, they're just a continuum matter density. On another account, there are just flashes, which means there is nothing, there are no particle whatsoever. So they're just a wave function and a certain number of flashes. And on that account, then of course when you do an experiment like the double slit, there is no particle going through either slit. Just the wave function, it produces something on the screen, which itself is not a real screen, but a set of flashes, and then there are differences in the statistics of the flashes. That I found also, to put it mildly, counterintuitive. And if you ask what the motivation for accepting such a theory, then the only motivation is really that it solves supposedly the measurement problem. It sort of gives a content to quantum mechanics, but that's already given by Bohmian mechanics. So I don't see why I should switch from that, from quantum. Also, that's an important point. GRW makes definitely different prediction from quantum mechanics or than Bohmian mechanics. But the problem is that there are adjustable parameters in the theory that for which we have no evidence whatsoever. We have no evidence for the values of those parameters. We can't test them. But we can adjust it so as to avoid being refuted by experiments. That's not exactly normal scientific practice to fix your parameters so as to avoid being refuted by observation. And I found, therefore, the theory, you see, I would be willing to buy the theory if there was an experiment actually showing, that quantum mechanics is wrong and the predictions of GRW are right. Then, of course, we would be forced to change, like we have changed every theory in the course of history. We always change theories if there is something wrong with the prediction of the old theory. But to the extent that Bohmian mechanics is quantum mechanics, it's not different, it's just a completion of quantum mechanics, then I would say that if we believe in quantum mechanics and we want to have a theory, then we believe in Bohmian mechanics and not in GRW, which is a different theory, which is done in an ad hoc way and which we would adopt if experience show that quantum mechanics is wrong and therefore Bohm theory is wrong and GRW is right. So these are the two competing theories, if you wish, but they are alternative theory, and I don't see why you should switch to the other theory just because they have adjusted their parameters so as not to contradict observation, while they would contradict the observation in principle.